Hello, welcome back to Mastering Statistics, Volume 7. What we're going to do now is start talking about the concept of ANOVA. This is a topic that is in the back of your statistics book. It's not difficult to understand, but there's a lot of components to it. So I want to give you a game plan here in the first lesson and give you an overview of what this really is. So I'm going to map it out for you. Basically, in this lesson, I'm going to give you an overview. I'm going to describe what ANOVA is in the big picture, right? And then over the next probably 3 or 4 lessons, we're going to calculate an ANOVA analysis by hand. It's not difficult, it's just tedious. So I'm going to show you how to do it so that you can really understand all of the formulas that go into it. Because ultimately you're probably going to use a computer program to do most of the problems in real life, like Excel, so Microsoft Excel. So what I'm going to do is teach you the equations and formulas by hand, at least with one long problem, so that you'll understand what the computer's doing. And then, most books just tell you to use the computer. So I could dump you in and just teach you Excel right now, press a button and get the answer, but you won't know what's happening or why it's doing what it's doing. So let's just jump into it now. You need to understand the concept of what's happening first. The big picture is that analysis of variance, even though it's got the word variance in here, and we'll talk about why it does in a second, basically we're going to be comparing population means, 3 or more population means. So I have a bunch of things I need to write down. I promise if you just kind of stick with me, even though you have to invest a little time up front, you will come out with a really great understanding about what this thing is actually about. So we need to compare, and you'll see what I mean by compare in just a second, 3 or more population means. So I'll call this population means. Now I need you to think back to hypothesis testing in many lessons ago. Recently we've been doing hypothesis testing with variances, and you'll see how that ties in. But even before that, we did population means, hypothesis testing with population means, but we were always comparing 2 means, right? Now we're doing 3 or more means, and we're all going to do it with one test. So in the past, we might have done see if population A or population B, which mean is larger. We write the null hypothesis, the alternate hypothesis, and we have the data, or maybe see if they're equal or not equal. Now we're going to be doing a test, a very specific kind of test with 3 or more population means. So let me just write down an example of a null and alternate hypothesis. Basically, the null hypothesis for these things are always going to look the same. Population mean number 1 is equal to population mean number 2 is equal to ... because I'm not sure how many populations you're going to have in your actual problem. It's going to be 3 or more. But anyway, it's either going to be equal to the kth population mean. So there's k populations here, right? And don't worry, I'm going to nail this down with a very specific example so that you understand what I'm talking about. But basically, the null hypothesis is that all 3, in case of 3 or more, however many you have, they're all going to be equal to each other. When you see notation like this is equal to this is equal to ... equal to the kth population. That means if I have 3 population means, they're all equal. If I have 16 population means, they're all equal. If I have 7 population means, they're all equal. That's the null hypothesis, that all of the means are equal. So if that's the null hypothesis, then the alternate or the test hypothesis basically means, the way that you write this down is usually in words, that at least, and I'm going to write this down very specifically, at least one mean, one of these means that we're studying, differs from the others. Differs from the others. Okay, so basically every single ANOVA, at least of the type we're doing here in this class, that you're going to do is going to have the same null hypothesis and the same alternate hypothesis. So you don't really have to do that much thinking in terms of how to set up the null and alternate. The null hypothesis is always the same thing. It means all of these means are the same. Okay, the alternate hypothesis is the test or the claim that the researcher thinks might be true, is that at least one of these means differs from the others. So what we're going to end up doing is, you might be thinking, well, this thing is called analysis of variance. Why are we comparing population means, right? That was my first question. The bottom line is, when we get into the math, you're going to find out that we're going to use the concept of variance in order to study the means. So even though we're actually studying means, the technique is called analysis of variance because we're going to be testing how these means vary with regard to the other means. So how does mean number 1 vary or differ from all the other means? How does mean number 2 vary or differ from all of the other means? How does mean number 7, let's say you had 10 populations, population number 7, how does that differ? Right? The populations can be anything. I could be studying human males on 7, different planets, if we have a big solar system, or maybe 7 different states. Those are the different populations. Maybe I'm averaging their IQ or something like that, and I'm studying, and each different location is a different population. So I'll have a mean coming from one area, a mean coming from another area, a mean coming from another area, and my null hypothesis is that all of these means are the same. They all have the same average IQ in the different populations, and so on. And the alternate is that at least one mean differs from the others. So we're going to be using the concept of variance to see how each of these means varies or is different from the others. Now, as we go through these calculations here that we're going to do, I want you to keep one example in your mind. I know I just mentioned studying people's IQs, but I have I think a better example that you can wrap your brain around. Let's say that we're a school administrator, and we have, lots of different schools, and we have 3 schools in my city, and I want to make sure all the kids are learning the same stuff. So I'm going to be testing them, basically. And so I have 3 different schools, school number 1, school number 2, and school number 3, and I want to basically I want to make sure that those test scores are coming out of that school, that the kids are learning the same things in math class, let's say. So as we go through a lot of these calculations, I want you to keep that in your mind. So I'm going to draw a couple of pictures here to hopefully make it a little bit easier. So the little cloud that I'm drawing here is the population. This is all the kids in school number 1. So I'm going to call it school number 1. See how clever I am? School number 1. So this is everybody in school number 1. So school number 1 might have 2,000 kids in it, right? That's a population. The cloud is the population, right? Now, also I have school number 2 because I have lots of different schools. So I'll call this school number 2. And then I have school number 3 over here. But keep in mind that analysis of variance is used when you're studying 3 or more populations. So this is a population of different children, this is a population of totally different children. But I could be studying all the schools in the country and have a bunch of populations, 10 or 20 or 50 or 1,000 populations, whatever. But now I'm just going to keep it simple, and we're going to do an example with 3 populations to make sure you understand the concepts. Now what we want to do is we want to figure out if these kids are learning the same thing in math class. So if we could test every kid in every one of these schools, if we could test every kid in school number 1, for instance, then we would get an average of their math test score from school number 1. Now this is a population. This is maybe 2,000 or 3,000 kids, right? So whenever I come over here and say, from this population, from everybody here, what do we get? If we could somehow know everyone's test score, right, then we would calculate a population mean. So the symbol mu is the symbol for the population. But we don't have money to test all 2,000 kids in school 1, and all 2,000 kids in school 2, and all 2,000 kids in school number 3. I forgot to put the number 3 here. Right? So we really never really know what the population mean is, because even if you say, well, you should test all the kids, I mean, I can choose a problem where it's really hard to test everybody. Maybe I'm studying everybody in the country. Maybe it's impractical to really give a test to everybody. Right? But anyway, if I somehow knew everyone's score, I would get the population mean from school number 1, their math score, right? School number 2, I would get a similar population mean. That's their average of their math exams. And then I would get a population mean of school number 3's test scores for math class. Now I'm a school administrator, so I want to make sure that everybody's learning the same stuff. So my null hypothesis, my kind of like my accepted hypothesis, is that mean number 1 is equal to mean number 2 is equal to mean number 3. Again, if I had more schools, it would be more populations, and I would say that they were all equal, because that's what I really want. Okay, so I want to say that my null hypothesis is saying that these population means are all the same. That's what the null hypothesis is. And the alternate, the test hypothesis, or the alternate that you're testing, is that at least one of these guys is different from the others, and that's really important to me, because if school number 2 has poor test scores, I want to know about it, right? Or if any of these schools have different test scores. But anyway, as we said, we cannot test everybody, so because this could be 10,000 kids. So what I really do is I go inside of school 1. So I'm drawing a little box inside here. What do I do? What do you think we do? We've been doing this stuff a lot. that I sample 10 kids. So let's say I don't have a lot of money, so I only sample 10 kids. I would like to know the actual population mean of the math test scores, but I don't have enough money or enough time to do that. So really I just take 10 of the kids, representative sample from that population, I put them in a room and I give them a test. And I take all 10 scores and I average those 10 scores. What do I get? From this calculation is something called the sample mean of population 1. Right? That's the symbol here. When you see X bar, that means a sample. That means I've taken a fixed number of people from the population, I've measured something, whether it's IQ, test scores, height, weight, whatever. Anyway, that's the sample mean, which is not truth compared to the population means really what I want to know, but I can make some inferences with a sample size of sufficiently large. 10 kids is probably not big enough, but anyway. That's what I do. And then I take that and I calculate a sample mean, X bar number 1. Then I go over here and I give the test again. I sample. I'll put 10 kids here. But you'll see that when we do the ANOVA, it doesn't have to be the same number of kids. I could only test maybe 20 kids here or 7 kids here or whatever. It all takes everything into account. And then from that, I get X bar number 2. That's the sample mean from school number 2, and then I do the same thing over here with school number 3. Sample. Again, I'll put 10 kids, but it can be a different number. And then from that, I get X bar number 3. That's the sample mean. So the idea here is analysis of variance is going to be a test that I'm going to be basically applying to the sample data that I got. The sample, that means the average, which is from a subset of the population, not everybody, a subset. And the analysis of variance test is going to take into account what these values are, X bar 1, X bar 2, X bar 3, the average sample means. It's also going to take into account how many samples I did in each population, because that's going to affect things. And then you'll see exactly what we do in a little bit, and then it's going to spit out an answer with a certain level of significance to tell you if this data that we used, if you can infer from it that the population means, which are different, the population means are everybody, are the same, or if they're different, which is what the null hype, or if one of them is different, okay? Now I want to point out to you, the first thing you might be thinking is, well, why don't we just do regular old hypothesis testing from a long time ago? Like, forget about school number 3. Let's say school number 3 isn't here. We can have school number 1, school number 2. We could do a hypothesis test to see if these means, X bar 1 and X bar 2, or if these population means are equal or not based on the sample data. We've done hypothesis testing like that. So we could do that, but then you have the third school. So then if you wanted to fold in the information from the third school, then you'd have to compare these two means, and then you'd have to compare school number 1 and school number 3 means, and then you'd have to compare school number 2 and school number 3 means, and then you'd have a bunch of different combinations, because when you do the regular hypothesis testing, you're only doing 2 populations at a time, comparing them. So even with only 3 of these guys on the table here, it's a bunch of different combinations, and you also introduce a lot of errors when you start doing a bunch of different testing, sequentially. Then what happens if you have 10 populations? You got a ton of combinations to do, and it gets very cumbersome really fast. So ANOVA lets you do 3 or more population comparisons at once, and you can draw some conclusions from that. Now, I have a few notes on my paper. I'm not going to write them all down, but I want to make sure you understand. I'm going to say them all to make sure that I've said them at least once. First thing is, we do not know what the population means are. If we knew what the population means are, which in this case is the math scores from each of these schools, then we wouldn't have to do any testing. We would know if they were equal or not, because we would have all the information. We don't know that because there's too many kids to test in a reasonable amount of time, or if you're studying entire continents or something, it's just impractical to do it. So what we do is we sample a subset of the kids, we calculate a sample mean, and we study these guys, and with a level of significance we draw an inference. So what I want to do is give you a couple of cases of what might come out of such a test. This is kind of like back of the envelope just to kind of get you to understand it. We're not doing the actual ANOVA testing. But basically there's a couple of cases that you can consider that are really instructive. So let's look at case 1. And they're kind of common sense too, honestly. What if you look at case 1 and say, what could possibly happen if the following happens? Okay, so over here we do the testing. Here's the score of 100. Here's a score of 80. let's say, right there. And then we get the sample means of each one of those 3 schools where we sampled and tested 10 kids in each one of those schools. So let's say the first school comes up with a score of X bar number 1, 81. That's the score that they got from school number 2. And then let's say, school number 1. Let's say school number 2 is really close to it. X bar number 2, 79. And then let's say this one's a little bit higher. I know I'm not drawing these exactly right, but you get the idea. X bar number 3, 80.5. So you can see that this guy, we'll call this school number 1, this is school number 2, this is school number 3. Now again, this is not the population mean. This is just from the 10 kids in each school that we gave the test to. So basically, the average of each of these test scores are pretty close. 81, 79, 80.5. To me, they look pretty close. So if you remember back, the null hypothesis is basically that the mean from school number 1 of all students, I should put a colon here, is equal to the mean of school number 2 of all students is equal to the mean of school number 3 of all students. That's the null hypothesis. The alternate hypothesis is at least one mean different. So basically that's my test. Now, of course, it all depends on the level of significance. It depends on a lot of different things. But to me, since this number is pretty close to this number, is pretty close to this number, this is likely. So in this case, we would fail to reject the null hypothesis. And that's all you're going to end up doing. You're going to circle that in your paper one way or another, just like any other hypothesis test. Either you have a null hypothesis and you reject it, or you have that null hypothesis and you fail to reject it. In this case, we fail to reject it because our calculations show, now we haven't done the actual test, but they look pretty darn close. Now let's just take another example and say, well, what would happen in the following case? Okay, so we'll look at case number 2. And again, I'm just doing this back of the envelope. So this is 100, this is 80. All right, so let's say what are some differences. Let me go flip the page here. Let's say school number 1 again comes in strong here with an X bar number 1 of 81. Let's say school number 2 is weak, comes in at X bar number 2 of 29.5, a really low average test score. School number 3 is up here at 80.5. X bar number 3, 80.5. All right, and again, this is school 1, school 2, school 3. Now, what do you think? Just basically just back of the envelope. Well, you can say, well, school number 1, school number 3 look like they're in line. That's reasonable. School number 2 bombed it, right? So this is a drastic example. Anybody can see this. And of course, I didn't even draw the bar graph correct. It should be down here somewhere. But I could change this number to, 65 if I wanted to, whatever. It's different from the other ones. So the null hypothesis in this case, same null hypothesis as before. Mean number 1, mean number 2, mean number 3. And the alternate is at least one mean different. All right, obviously, to me it looks like one of these means, in this case school number 2, is different. So in this particular case, this is unlikely. And so at the proper level of significance for your problem, you could reject the null hypothesis. I'm just doing this for you to show you that the ANOVA testing is going to give you the same answer as any hypothesis test. Either you're going to reject the null hypothesis or you're going to fail to reject the null hypothesis. Now, there's a couple of notes that I need to make sure you understand before I close this section out. First thing is we study the population means of the students in the school by sampling, by taking a subset of them and calculating things and drawing conclusions based on that, right? We're going to end up using variance, the concept of variance, to see how these means differ from one another. And it's impossible to explain that to you without showing you some math, so I have to do that in the next couple of lessons. But we're going to use variance. That's why it's called analysis of variance. But don't forget, we're studying the means, how the means are different, okay? The test here, the ANOVA test, tells us if one or more of these means are different, but it does not tell us which one is different. Now, in this case, it's obvious. This one's the different one, right? But it's not going to be so obvious if you have 10 populations and one of them differs by just a little bit statistically. You're not going to be able to eyeball it. I've drastically made this one different so that you could easily see what I'm talking about. But the test either tells you if they're all the same or if one of them's different. It doesn't tell you mean number 1 is different or mean number 2 is different. That's beyond the scope of ANOVA. You'll have to do additional testing and study to figure that out. So that's an important thing. The other thing I want to allude to, I'm not going to get into it too much here, but basically the validity of the test kind of depends on the data that you sample to begin with. I mean, we're doing all of this calculations based on the 10 kids that we looked at in school 1, the 10 kids that we looked at in school 2, and the 10 kids that we looked at in school 3. So as we do the ANOVA test, the number of kids, number of samples, is going to influence the outcome, right? Also, we'll find out later that the quality of the data affects the outcome. So if, for instance, in school 2 clearly was having a bad day, but is this average of 29 because 2 of the kids got a 0? And maybe 8 of the other kids did great, but 2 of the kids got a 0. Maybe 2 of the kids just ripped the paper up and threw it in the trash can. So if you have a bunch of outlier data, garbage data, out of the samples from school 2, it can cause the average from the sample to look weird and different, but it may not be indicative of a really bad population. What if they had a fire drill that day? Or what if the teacher giving the test had the cold or something? Or anything could happen. What if a meteorite came in through the roof and disrupted the classroom? Then everybody did bad. So I guess what I'm trying to say is, yes, you can draw conclusions, but don't just turn your brain off. You have to look at the data. And the ANOVA test does look at the quality of the data. It does look for outliers to see if any of that's going on, and it will automatically adjust the conclusions accordingly. We'll get there when we get there. I just wanted to point that out to you. That's the concept of analysis of variance. Basically, all we're going to be doing is studying means, different population means, and we'll do that by methods of sampling. We'll take a sample from each of the populations, calculate a sample mean, run it through some calculations, and go from there. So I'm going to do those calculations in the next several lessons, and then I'm going to show you how to use a computer to do it, and you'll see why computers are used, because there's just a lot of numbers to crunch. So make sure you understand this, follow me on to the next lesson, and we'll get started.